Okay, so today we are going to continue to learn this amazing piece of software called database. If you look at what we have been doing in the last 4 lectures, right? So pretty much we try to think about 2 questions. First one is I have data, right? How should we think about it, right?
You're muted, Professor Song.
Yeah, so how should we think about our data? Essentially the data model, right? So there are so many potential ways that you can actually model your data, and one specific way that we are going to be focusing on.
Could you unmute yourself, please?
Really? Okay. So one specific way that we are going to focus on in this course is by thinking about data that as something that can be fit into a whole bunch of tables or relations, right? So there are multiple ways you can think about it. You can say, yeah.
Sorry, you're muted.
Oh, okay. Can everyone on Zoom hear me? Okay. Yeah, sorry, I was muted on Zoom. Sorry. Yeah, that's why they they try to get my attention. It's my fault, not their fault. Okay. Sorry. Okay, so we are lucky because we just started. Okay, so hi everyone, let's get started. Everyone on Zoom. Yeah, so today we are going to continue to talk about essential database, right? So if you think about what we have been doing in the last 4 lectures, we pretty much try to understand 2 fundamental questions. So we want to manage our data. So the first question is, how should we think about our data? What is our data, right? So in this course, we are going to focus on one specific way of thinking about data is by thinking about them as something that can fit into a whole bunch of tables, a whole bunch of relations. So even that, there are multiple ways to think about it. You can think about that as a collection of tuples, right? And you can manipulate them using kind of set operations. You can think about them as a whole bunch of facts that you assume to be true. And then you can actually query them using mathematical logic. So this is a relational model. Once you have your model of your data, you can start to define the ways that you can query it to extract insight from your data. And that is a whole bunch of query languages that we have been talking about. So just to refresh our memory, what is a query? Right? So query is a function that takes as input a database instance, which is a whole bunch of relations, contains a set of tuples or facts, and output a new relation. Okay, so that's the definition of query in our, essentially, in relational model. And what is query language? Query language is simply a specific way that you can specify a query. And the power of a query language is like essentially being defined by the set of functions that you are able to specify using that query language. And we have been talking about a whole bunch of query languages. Let's just go through them one by one and to make sure we are on the same page. We talk about relational algebra, right? So what do we mean by this? So in this way, we are thinking about relation as a set of tuples. Because it's a set, there's nothing stops us from querying them, getting new relations by using set operations. In relational algebra, we define a language that contains a whole bunch of set operations, for example, selection, projection, renaming, or different type of. Okay, so yeah, so and then each one of them has a signature that takes as input 1 or 2 or 3 different relations and output a new relation. And because of that, you can stack them together to form a relational algebra expression. It's very simple. And we talk about another query language called Relational Calculus. It's kind of very different from relational algebra because instead of treating a relation as a collection of tuples, we start to treat them as a collection of facts, or we start to treat them as a first-order interpretation in a logic system. In this way, you can start to query your data by simply writing a logical formula, and then you say, yeah, I want to find all the models of that formula that's true under my database. So that's a different way for you to query your data. We also talk about the relationship. We also talk about, which one is more powerful, right? So in this case, if you talk about relational algebra, relational calculus, right? Relational calculus is actually more powerful than relational algebra because in relational calculus, you are able to define some query, output infinite amount of tuples, right? But in relational algebra, given a finite database, you always have something finite. And we always talk about, and we also talk about how to constrain the semantic of relational calculus. We talk about another query language called domain-independent relational calculus. It pretty much by introduce a notion of active domain, right? To say, so I don't want you to output infinite amount of result. What I want is you can only use all the constant that appears either in the query or in the relational database instance. And then you have something that is kind of equivalent in how powerful they are with relational algebra. And we also talk about different subset of these two query languages. We talk about the subset of relational algebra that only contains selection, projection, join, and renaming. And we also talk about conjunctive query, that you can only write conjunctions in your logical formula, and then they are also equivalent, of course, less powerful compared with relational algebra and domain-independent relational calculus. So this is on the theory side. In the last lecture, we also talked a little bit about how to do this in a practical way. We start to introduce a practical query language called SQL. We also start like step by step. We talk about what you can write using a very single construction called select from where, which allows you to write pretty much everything you can write in this relational algebra subset. And we also talk about a larger SQL subset, contains union, contains intersection, all the type of things, which allows you to write whatever you can write in relational algebra. And we also start to talk about the things that you cannot write in relational algebra, but you are able to write in SQL queries. For example, aggregation, right? So last lecture, we talked about how to deal with incomplete information, right? So in this lecture, we are going to continue to talk about things that you are able to do in SQL, right, in practice. So specifically, we are going to talk about 3 different new concepts. The first new concept that we are going to talk about is something that's called views. So why should we talk about this? If you think about what we have so far, right, you have a piece of data, right, and then you have a whole bunch of relations, right, which is your model of that piece of data you have. If you think about the power of a database system, it gets its power because we keep introducing those high-level abstractions for you to talk about data, right? So if you do not have a data model, all you can do in querying your data is by writing some, like for example, Python script or like a Java program, right? But once you model your data, you start to introduce some independence between your query and your data. For example, inside like database system, we are writing a query against relation. You have no idea how the relation is being stored. You don't know which tuple is stored first, which tuple is stored second. You don't know how they arrange on your hard drive. You don't even know whether they are on your hard drive or inside your main memory, right? When you are writing a SQL query, you have no idea how the data are physically organized. And that's really a beautiful property called the physical data independence. But one question we are curious about is, can we do more? Can we introduce even higher level of independence between your query and your data? So now let's think about this. Given the SQL query that we know how to write in the last couple lectures, what dependency do I have between the query and the data? As a user, right, when I write a SQL query, what are the things that I need to worry about? So one thing that I need to worry about is, of course, when you write a SQL query, you are assuming your data is organized in a collection of relations, and you are assuming that is something that's fixed, right? If you have like relation, for example, students, contains the ID of the students and the name of the students, and also which semester the students like it's in. You are actually assuming you have one relation contains these 3 different attributes, right? But that's not the unique way of storing that piece of data. I could store them in, for example, 2 different relations. I can have one relation store the ID of the student and the name of the students. I can have another relation store the ID of the students and also the semester of the students. If you do that in that way, your SQL query start to break because you are making some assumption of how data are being organized into some relations. You are assuming the schema of the relation is something that you know. In many cases, that's okay, right? So I mean, there's nothing wrong about it. But in some applications, it is actually useful for us to introduce some even higher level of independence to make sure not only I don't need to know how data is being physically organized, I also have some flexibility to not knowing how data are organized into a relation. And that is what we mean by view. The goal of view is really give you an even higher level of abstraction to provide what we call logical data independence. So that is, whenever you are using view, you do not need to care about how relations are organized underneath the cover. Maybe you have one relation with ID, name, and semester. Maybe you have 2 relations storing different pieces of information. When you are using view, our goal is as a user, you even do not need to worry about that. Okay? And that is something we are going to look at about what to do. So essentially at high level, if you think about how we enable this like pretty magic functionality, the way that we are trying to enable it is we think about a view as some SQL query that you stored inside your database, and you can just query the result of that query as if it is a table. So let's become a little bit more concrete. So how to define a view inside database system is actually very similar to how you define a relation or define a table. So instead of create a table, right, you create a view with the name of the view. And instead of defining the schema, right, of this view, as if you are defining a table, you have one SQL query to define this view. So the semantic of this is I'm defining a view with this name. You can query this view as if it is a relation or as if it is a table. And what is the content I should fill in to this view? The content I should fill in this view is the same as the result of that SQL query. So that's a semantic of a view. And then you can use this view as if it is a table when you write other SQL queries. So there's a fundamental difference between view and table. We are going to look at that relatively soon. But let's try to look at how to use a view. For example, I have a relational database look like this. It contains all the flight information, okay? So there's the source, there's destination, there's the price of the flight, for example. There are different airports. I could define a view that looks like this. I could say, yeah, so let's try to get all the flights from a certain airport, for example, PK, right? And they'll say, okay, I create a view with the following name, flight from PK. This view is defined as a query, and this query is select star, select all the attributes from flight where the source equals to PK. Okay, I get all the flight that originated from a certain city, and I put that in your view. Once you define this view, you can treat it as a relation. You can then write the SQL query look like this. Okay, let's start from this view as if it is a relation, right? Where the destination equals to another place, right? In this case, right, you are going to return, in this case, I think, a single tuple, right, as the answer of this query. So if you think about what database is trying to do is, once you define this view, what is the content of this view? The content of this view is something that you have on the right-hand side. That is, I define, so because that is the answer of that query, right? And you give the name to that table on the right-hand side. And whenever you are writing a SQL query, right, you are just get the answer like this. This looks very similar to a relation. But if you think about what is the fundamental difference between a view and a relation, is on the right-hand side, that relation is never materialized. In the sense that, assuming your original table that we call base table start to change, you insert some new tuple, all those type of things, the result of the view will automatically change because that thing never gets materialized. Okay? So this difference can be made really concrete when we look at one example. So let's still take this relation. Now let's compare two different collections of SQL queries. On one hand, we define a table on the left-hand side. And on the other hand, we define a view. And we can run the same collection of SQL queries, right? So you define the flat from PK as a table. And then let's try to insert a tuple into the flat table on the left-hand side. And then you run another SQL query. What would we get in this case? Essentially, that SQL query tries to get all the flight from PK to Zurich. And in the original table, I have one flight, right? So that's the first tuple, PK to Zurich, price 100. And after you define the table, you insert a new flight, PK to Zurich, 200. And now I say, yeah, I select all the flights from PK where destination goes Zurich. How many tuples are we going to have? Who think we get 0 tuple, 1 tuple, 2 tuples, 3, 4, 5? No? Okay. So in this case, you get essentially 1 tuple, right? If you think about why, is this flight from PK table, once it's getting created, it doesn't matter what you put into the flight table, right? Because once you create that table, it's being materialized inside your system. It's never going to change unless you manipulate it directly, right? It starts to lose all the provenance you have inside your system. The system doesn't know it's being generated from the flight relation. Now let's look at the thing on the right-hand side. So here, instead of creating a table, we create a view with the same name, defined by the same query, and we do the same thing. We insert a tuple inside the flight relation, and then we query this view. In this case, how many tuples are we going to get? Who thinks 0, 1, 2, 3, 4? Okay. So in this case, you are going to get 2 tuples. If you think about why, is this view never gets materialized. View is only being materialized, or that query is only to be run when you use the view. Okay? So essentially, when you query this view, select star from flag from PK, right? When you query this view, that is the moment this view gets executed. Okay? And at that point, in your source table, you have 2 flights from PK to Zurich because I just doing the insert before I'm using this view. Okay? So that's a fundamental difference. The moment you are creating a table, you already materialize all the result of that query and put them into your database. If you make any changes of your base table or source table, right, that new table will never change. Once you create a view, you give the database some logical statement about what is information that you want, and the moment you use it, the database is going to rerun that SQL query to get that information. Okay? So that's a fundamental difference between table and view. So why do we want this, right? So there are multiple use cases for views, right, compared with table. So first application is to really control like permission or really ensure privacy of your data, right? Because whenever you have a database, your assumption is always there are many people have access to your database. But the problem is that not all of the people having access to the database have the same permission, right? So even for the same table, right? For example, you have this flight table, and you want to create a view like this, right? So assuming you have some secret flight, right, that you don't want everyone to know. Only some admin knows about that flight, but all the other people, right, do not know the existence of some other flight, right? In this case, you can actually try to give the permission of this view to that subset of people instead of giving the permission of this base table to all the other people, right? If you want to say, okay, here's a group of people, they only have permission to view all the flight from PK for whatever reason, you can just say, okay, this group of people have the permission to read this view, but not the base table, okay? So this starts to give you those functionality or permission control, to access control, to make sure you can manage who have access to which piece of information. If you only have a single base table without view, oh, that could be super hard to do, right? You need to give people permission tuple by tuple, right? That's either going to be slow or whether or going to be very tedious. So just like another example, right? So for example, we are manage all the information of the students, right? So there's the ID of the students, there's the which lecture each student take, and also the grade of each student. Ideally, right, you want to be the only one who knows your grade, right? You don't want other people to know the grade. But there are so many different applications having access to that database. We need to separate who have access to each student's grade, right? In this case, the ones you could do is you say, yeah, there's some user who can know which student take which lecture, but they can never know their grade, for example, right? In this case, you can create a view to project out the grade attributes, and then you give those users the access to this view instead of that base table, right? So this gives you a very easy way to do access control inside your database. And sometimes you use view because it simply makes your life easier, right? So by using view, you could say, yeah, once I define this view, a whole bunch of other queries are much easier to write, assuming I have access to that view, right? For example, in this case, if you define this view, right, flight from PK, and you'll say, yeah, let's try to find all the flights from PK to Zurich, right? How to write it with this view? Yeah, you say, if you do not have this view, you need to query the base table. You need to write down all of those conditions, right, there, right? So if you have this view, your query becomes shorter, right? So in this case, right, so there's not that much difference between these two, but in practice, when your SQL query could be 100 lines long, right? So having some predefined view can often make your SQL query much, much easier to write, much easier to read, and much easier to manage, okay? And there are other kind of use case that you could want to use view, right? For example, you can actually use view to essentially try to identify those generalization relationship between multiple entities. For example, I have this database. I want to store all the employee relationship, right, in a university. I could have one table contains all the employee information, such as the ID, the name, for example. But there are different type of employees, right? And they have different type of attributes. So how should I represent all those information? And there are multiple ways you can do it. One way is, okay, I put all those common attributes for employee into the employee table. And then I say, yeah, there are also professors. Professors have, for example, another attribute, room, for example. Yeah, then I have another relation, only store that piece of information, okay? And I have, for example, teaching assistant, for example, which contains, for example, some attributes, say, which course, right? So the student is a teaching assistant, right? Then I could store that piece of information into another relation, right? Assistant data, right, with that. If you store your information in this way, one problem that you could see is now my information is kind of in different pieces. If I want the information of a professor, I should always join the employee and the professor data table, right? If I want the full information of professor. Assuming that is something you use a lot, the thing you might want to do is to have a view there to actually say, let's define a view that contains all the professor information. The definition of this view is by drawing this employee relation with a professor data relation. And then if you query this view, it's going to give you all the information we have about the professor. And then you can say, yeah, let's also define a view about assistants, right? By drawing this employee relation with the assistant data relation. And whenever you are querying this assistant relation, assistant view, you're actually getting all the information. You don't need to draw it manually every single time you want the full information of the professor. However, underneath the cover, the information can be stored in relations that in a fractured way, right? So it could be like in different relations. And you can also do the other way around, right? So another thing you could do is, okay, let's think about the same use case. I have a professor, I have an assistant, I have an employee, right? So one thing I could do is, okay, I could have a professor table, contains all the professor information. I could have an assistant table with all the assistant information. And then I have other employees who are not professor, not assistant. I only store, for example, ID and name. You can organize your information also in this way, right? This gives you the same, like this model, and this could model the same piece of data. And what if you want the professor information, right? So in this case, you can just query professor. What if you want assistant? You can just query assistant. What if you want to query the employee relation, right? You can actually do a union between these three relations, give you this employee view, which contains the same information as we would have in the previous slides about all the employees. So as you can see, this is actually two examples that you are actually trying to organize the same piece of information. Whole bunch of employees, some of them are professor, some of them are assistant, some of them are other employees. This same piece of information in two relational schema. The first one is I store employee and all the employee information, and then store the special attribute for professor, store the special attribute for assistant. The other way is I store all the information for professor, all the information for assistant, and other employee, right? They store the same piece of information. By having a view, you can actually query these two databases using the same query, right? Because you can try to reconstruct the employee relation by defining a view if it's not here. In the previous example, you can reconstruct the professor relation, the professor information using the professor view. This is what we mean by view give you something, provide logical independence. Because when you are writing this query, by using view, in principle, you actually do not care how the information are organized into tables. It could be organized in this way, it could be organized in the previous way, but when you're writing a query, the same query should run in both relational database instances. So that's one example that why we really want view. So another thing that's interesting is once we have view and once we query the view, how does the view get evaluated, right? So this is relatively easy to say. It's very hard to implement a database system, but very easy to show on a piece of slides. That is, what database is trying to do is once you have the view, it's going to rewrite your query, okay? So let's say we have this relation, right? I create a view, and I query the view. What happens underneath the cover is the database going to say, yeah, I know this view is nothing more than a name for a query. When you are querying this view, essentially, you are asking me this query. I just replace, right, the name of this view with the real SQL query that you defined. And then the system is going to rewrite this query automatically for you to say, yeah, this query actually equivalent to that thing, okay? And as a user, what you are trying to do is try to deal with the view, and what the database try to do is try to expand the view, replace the view with its definition, and just run that query for you, okay? Just a whole bunch of research about how to do this efficiently, but as a user, right, you don't need to really care about that. You get this high-level functionality for free, and database try to do all the work for you. So in principle, this is how view getting evaluated. By the system automatically rewrite your query. So before we talk about how to update a view, any questions about view? The definition of view, how to use a view, why do we want to use a view, and how it's get evaluated inside database? Any questions? Any question on Zoom? Okay. Now let's talk about another thing, right? So assume you have a database, and all my information are inside the table or relation, and I could update it. I could delete a tuple, I could insert a tuple. We all know how to do that now. A view would look very similar to a relation, right? Can we update it? Can we update a view? Can we say, yeah, I have a query, this is a view. I know you have that tuple in the view. I don't want that anymore. I want to delete that tuple from the view. Can we do that? So this is actually a pretty fundamental question, because if we phrase the question in this way, we have no idea what we really mean by that, right? What do we mean by really update a view? There could be multiple ways that you define what do we mean by updating a view, because it's something logical, it never exists. What do you mean by updated? So we focus on a specific way to defining how to manipulate a view by taking the following perspective. Assuming you have a whole bunch of base relation, okay? That relation inside a database, R1 to Rn, and you define a view over this base relation using query Q. And now I say I want to manipulate this view. So what I mean is I want to manipulate my base relation such that if I run this query on the manipulated base relation, I get a new set of results in this view that reflect the change I want to make. So essentially, I have this base relation, I define this view, and I say, okay, I want to change this view from V to V prime in terms of its result. What we really mean by that is I want to change my base relation from R1 to Rn to R1 prime to Rn prime such that if you run the same query over the updated base relation, you get a view that I want. You get a set of tuple that I want in this new view. So this is actually what we mean by actually update a view. So let's look at one concrete example. So assuming we have this flat relation, and then assuming we have this view, right? It gives you, if you evaluate it on that relation, you get something like this, right? So here we now have three flights here. And you'll say, okay, I want to delete this tuple from this view. I want to delete all the tuple in this view where price is higher than 500. Essentially, what you want to do is you'll say, okay, I really do not want this tuple in this view. But what you really mean, at least what we hope you really mean, is I want to manipulate my base relation to delete this tuple such that if I run the same query, my result will not have the third tuple in the view. So that is essentially, in principle, what we mean by running update query or insert query over a view instead of over a table. Of course, there could be other ways you can define what do we mean by update view, but this is one of the most traditional way or popular way to think about it. But if you take this view, right, so there is one question that's just follow immediately after this, is if you think about the manipulation of a view as a manipulation of the base relation, it's very easy to see it's not always possible or not always unique, right? Because you tell me what you want as a result, maybe there are different ways that I can manipulate my base relation such that I give the same thing, right? Maybe there are, maybe I cannot even find such a way to manipulate a base relation to give you what you want in this view. So the consequence of that is actually not all the views can be updated. and not all the updated query is valid over a view. So we need to be really careful about what you can do over a view. So now let me give you one example about a view that's not really updatable. Okay? So let's assume you have this relation. Okay? So it's you have, for example, one relation about students applied to universities, right? So you have student ID, you have the name of the student, you have the major, you have the application decision, for example. And I have a view to say, yeah, this view contains all the students applied to computer science, and the decision equals to yes, something like this. This is all students I have. And then I want to insert a tuple into this view. In this case, as we can see, it's super hard, right? Because in this view, all you have is student ID, because that's your projection, right? So that's what's in the view. If I insert something into this view, there are so many different ways I can manipulate my base relation, right? Because you never specify what value I should fill in for all the attributes that I projected out when I define this view. This is one example of a view that's not really updatable because I don't know what to fill in, right? So there are so many different ways I can manipulate my base relation to get what you want, but I don't know which one is the right one. So as a database system, I try to be really conservative. Yeah, I'd rather not to update this for you, right? And there could be other examples. Aggregation could also be hard. So let's think about this very simple relation, right? So I have a single column inside this R relation, and I have number 1 to 9. And I define a view to say this is the, I define a new view that contains the sum of all the values. I could define this view like this. I create a view V as select sum R from R, right? I have aggregation. So assuming I want to update the view like this, I want to update the view such that the value of the view like sum equals the sum plus 1. This is super hard to do, right? Because there are so many different ways I can manipulate the base relation to make this happen. You want the sum to increase by 1? Yeah, I could change the first tuple from 1 to 2. It's fun. I can change the second tuple from 2 to 3. It's fun. I can insert a new tuple into this, like equals to 1, then it's fun, right? So given what you want, there are so many different ways I can update the base relation. It's not really unique. So when that happens as a database system that manages the integrity of your data, I'd rather do nothing. I'd rather say, okay, I cannot allow you to update this view because I don't know how to update the base table for you. So this is something that kind of gets a little bit complex when you think about a view, especially when you think about how to update the view. But also there are views that are easier like, to update, right? So we look at a lot of hard case. This is an easier case that is a view clearly can be updated. So assume you have these two, like one relation with two different attributes. Your primary key is the first attribute, R, and you have another attribute, C, in this base relation. And you define a view as a projection. Right? You project out the C attribute. You only keep the primary key of this relation. In this case, you'll say, yeah, let me up this view. I want to delete a tuple where R equals to 5. This clearly is updatable, right? Because all I'm doing is keeping all the tuples with the primary key, equal, keeping the primary key, and now you want to delete the tuple where the primary key equals to a certain value. There's only one way I can update this relation is by deleting the corresponding tuple where R equals to 5, right? So here you have this almost one-to-one correspondence between a tuple in your result of the view to the tuple in the base relation. And if you want to remove a tuple in the view, yeah, you know which tuple to remove in the base relation to make it happen. And because of this one-to-one correspondence, there's a unique way for you to do that, okay? So this is actually another example for a view to be easily updatable. So inside the database system, when we talk about the practice, the whole thing becomes a little bit more complex because not only we need to think about what is in principle, all the views can be updatable, we also need to think about what we actually allow our user to do because maybe it's too expensive to support all the views that can be updated. Maybe we only want to support a simple subset. Right? But the principle is clear, right? We want to support all the views and all the updates such that it's easy to find the corresponding updates on the base relation to reflect the updates you want to have on your view. So inside your database system, right? So the principle is the system try to make sure the answer is deterministic. It doesn't really want to have the case where you ask the same query, you have same update of view, I have different possible strategy of the base relation, and I pick a random one, and if you run the query twice, you get a different answer. We don't want that, okay? We want the whole thing to be unique, to be deterministic, and we want to be conservative in the sense that I only manipulate your data only when I'm sure that's what you mean, okay? So when really try to support this functionality of the system, this is the two principles that we have to take. In practice, if you look at the SQL standard, a view is updatable if and only if the following condition hold. That is, the view involves only one base relation, okay? There's no join, just one base relation. The view involves the key of the base relation to make sure you have this one-to-one correspondence between your base relation and all the tuple in your view, okay? It's involve the key. And this view doesn't involve aggregation, doesn't have group by, doesn't have duplicate elimination, all those type of things, to make sure you can keep this one-to-one correspondence. So in SQL standard, this is what we mean by a view to be updatable, okay? If you think about the intuition behind these three rules, right? So there's a one-to-one mapping between input and output, and then I can implement your update on this view efficiently and also correctly, okay? So essentially, if you take all the views, all the possible views you can write inside database system, right? Only a subset is updatable in theory, and only a smaller subset of that is what you can actually update inside SQL, okay? So this is all about views, right? Let's take a break, and when we get back, we are going to talk about something really interesting called recursion. Yeah. Okay, so let's continue. So people on Zoom, can you hear me? I didn't forget. I mute myself, right? Perfect. Okay. Okay, so let's continue. Have this. Okay. Yeah, so before we start to talk about recursion, let's try to look at one example about updatable view, right? So we got a really good question during the break. So let's look at this, right? So on the left-hand side, so I have a very simple SQL query. I create a table with two attributes, A and B, right? So A is an integer, B is an integer, and A is a primary key, okay? So, and then on the left-hand side, I run the following SQL query. First, I just build the schema. So I run the following SQL query. I insert two tuples into R, right? The first tuple has value 1 and 2. The second tuple has value 2 and 3. After insert two tuples, I have two tuples in this relation, right? And then I create a view, only keeping the primary key, and project out everything else. I create a view, right? I select A from R. If I select if I select things in this view, right? What would I get? I get 1 and 2, right? And then I insert into this view by only specify the primary key. The question is, if I look at my base table, what would we get? Right? So is the setting clear? Okay. So I have a view. Project out everything else other than the primary key, and then I insert into this view by only specify the primary key, what would happen in the base table. So in this case, if you build a schema, if you run this SQL query, how many tuples will we get? Oh, okay. First one, like, will the system throw an error? Who thinks the system will throw an error? Who thinks the system will not throw an error? No? Okay. So what would be the value you think we will put into the other attributes? Yeah. So in this case, if you run this, you are going to get this is your view before updates. This is your base relation, right? So you put a null here, right? And then we talk about a view being updatable, saying that it involves the key, right? A very good question is what does that even mean, right? So for example, if I write a SQL query look like this, does this involve the key? My view is select everything from the data. My information is I select the key multiplied by 0. And that involves the key, right? And that has a key there, right? What would happen if you run this query? So the change is clear, right? I just put this thing here. Who thinks the system will have error? Who thinks the system will do the same thing? No? Okay. So yeah, it will actually throw an error because database is not that stupid, right? So I mean, oh, why? Yeah, see, this one got stuck. How to stop? Okay, you run it at home, it will throw an error, okay? Trust me, for some reason it got stuck. Yeah, so this one will throw an error. So essentially when we talk about an update view need to involve a key, we don't mean that in a syntax level. It's not like you put a key in the view, it's fine. It doesn't work like that. It need to be able for the database to recover this one-to-one correspondence for the view to be updatable. And that's what we mean, okay? Okay. It's still stuck for some reason, okay. Okay. Now that's all about view. Oh, okay. Something went wrong, it says. Yeah, sure, because not updatable. Okay, recursion. Now we talk about views, we talk about a whole bunch of things we can do in SQL. Now we think about its limitation, right? Can we construct a query that we are not able to write using everything we have been learning in the last 3 weeks? Right? What have been learning, right? We know select from where, right? We know aggregation, we know subquery, we know null, right? We know views. We know quite a lot of things now, right? Can we think about a query that we cannot write using all of this? So that goes back, if you remember, like 2 weeks ago or 1 week ago, we talked about the limitation of relational algebra. That's actually the same query. So assuming I have a relation look like this, I have a parent and child, this relation. I want to say, yeah, give me all the ancestors of a certain person. Now we know how to write a SQL query now. How would we write that? Let's think about it. So how to get all the parents of this person? And that's very easy to write, right? So I hope everyone knows how to write it now. You select the parent from parent of where child equal to D, something like that, right? You get all the parent of D. You got this in this relation. Now let's try to get grandparent of D, right? So what do we have, right? I join this parent of relation with itself, right? I select from parent of, give the name P1, parent of P2, right? I say, yeah, so I join them for the first parent of, the parent equals the child of the second parent of, right? That gives you the grandparent of D. In this case, it looks like this. I can get the great-grandparent of D by drawing this relation 3 times. Now get something like this. But none of this gave you the answer to that query, right? Because I don't know how many times I need to join. Whether this query gave you the right thing depends on how many levels I need to go up inside my database. And that is not something that I know, right? So essentially, this is a query that's very hard to write using all the things we have been learning so far. It's very hard to write a single SQL query. Again, single SQL query, it's not like that you can write a SQL query, compute how many levels, you remember that value, and you write another SQL query. It doesn't work like that, okay? So you have a single SQL query. It's very hard to write a single SQL query to answer this that works for all possible database, because you simply don't know how many levels that you need to go up. And this is a fundamental limitation of what we have. So let's try to fix that. So this is another query that's kind of hard to write. Again, this is our flight database. There is the source, there's a destination, there's a price of the flight, right? If you think about what information do we have here, it's pretty much define a graph, right? So every single constant in this relation corresponding to a city, there are nodes in the graph, and every single row in this relation corresponding to one edge in the graph. For example, you have the PEK to Zurich, the first row, right? That's corresponding to essentially one edge in the graph from the node PEK to the node Zurich. Essentially, that relation is trying to kind of define or try to express this graph. Now I say, yeah, so the query I want to write is what is the cheapest way to get from city 1 to city 2? How to write that query, right? If you think about how to write that query, it's also pretty hard. I can get the cheapest way if you take a direct flight, right? That's easy, right? So I can write an aggregation query to say, yeah, I select all the source or destination, satisfy your constraint, I aggregate them and pick the mean, right? This is the cheapest flight you can take. That's nonstop. But there are other things that you could do. I mean, you can do one-stop flight, right? You can say, yeah, I join this flight relation with itself, right? I fly from city 1 to city 2 to city 3. I introduce a join condition, I introduce the source and destination constraint, and then my price is, for example, in this very simplistic case, right, it's the price of flight 1 and the flight of flight 2. I do the aggregation. You could do that and give you a different flight. But this still doesn't answer your query because I'm asking what is the cheapest way. I mean, it's not the non-stop, it's not the one-stop, right? So in principle, you can have 100 stops if you can have a cheapest way, right? So the problem of this is, again, I don't know when to stop, right? If you give me a constant number of stops that you want me to do, I know how to do that. I'm going to have a very long query, but I know how to do that. But if you say, give me all the possibly infinite amount of stops, that I don't know what to do because I don't know how to write a SQL query that's not of a finite size, right? And that's a fundamental limitation. We never introduce a similar notion, for example, like a for loop in Java, in C++, or in Python. We don't know how to write a for loop. That depends on the data. And that is a fundamental limitation. So that gave us a functionality called recursion that we really want to support inside our database system. And the observation is, what do we mean by that? The functionality we want to support is like this. We need to run the same query again, and again until the result doesn't change. That's pretty much the functionality that we want. If we have this functionality, we are able to answer all the previous two queries. So for example, if I have this functionality, right, what do we mean? We want to find all the ancestors. What do we have, right? So essentially we say, yeah, let's try to get all the ancestor 1, right? So this is a first level ancestor. And then I join this ancestor 1 with the parent of. I get the second level ancestor. I join ancestor 2 with parent of a very similar query, but just with a different stage, right? I get the third level ancestor. I keep doing this. At some point, your result will not change at all because you reach the root of the family tree. So that's when I want to stop, and that's when I want to return, okay? So we are going to make this very precise about functionality we are trying to enable, but intuitively, this is what we want inside database. We want the ability to run the same SQL query again and again until I cannot extract new information from this data anymore. That's what I want. Now again, like you can, so if you look at this, right? So there are multiple things that you should do. Essentially, you should define the base query, the first query, to make sure the system knows how to start, right? You have this recursive query, the thing you want to run again, again, and again. You check the convergence, and you return. So that's the three different components we want. If you think about what do we need from the user, if you try to design a database system, yeah, we need the user to give us the base query, right? So that's the initial thing in that relation. And also the recursive query. Yeah, system knows how to check convergence to make sure it doesn't change, it's fine, right? So that's actually gave us the syntax of this. Inside database, you can write something like this. You can have the with statement to say with recursive R. R is the name of this recursive relation. Defined as following, you have the base query, union recursive query, and then after you write this, you can write another SQL query just as R, using R as if it is another relation. Okay? So essentially, this gives you a way to define recursively what a relation is. Okay? So how does the database try to run this query? When database try to run this query, it's very simple. It's first set R to empty. The starting point is this R is empty. Okay? And then it's try to run this base query union recursive query once and set it as a new R, and then run it again, until the result doesn't change. And then the system allows you to run the last row, which is a query involving R. Okay? So this is just one example about how to write a recursive query, try to find all the ancestor of a certain person, right? In this case, you have a recursive query, define a recursive table called the ancestor of D that contains all the ancestors of D. It defined as union of two queries. You have the first query, right? I select the parent from parent of where D equals to this child, right? In this case, you know where to start. I mean, you actually take the first level of ancestor, and then you have the second recursive query that essentially join this ancestor of D relation from previous step with the parent of relation, and then get the next level ancestor. So this is actually one way that you can do. And then in the last row, in the last row, can select star from this recursive relation. Okay. So it's very long, right? So it's very tricky. So there are a lot of things that you need to consider. So let's look at some simple examples, okay, to make sure we understand the behavior of the system. So let's assume you have a query that looks like this. It's the simplest recursive query that I know how to construct. You define a recursive query look like this that gives you a recursive relation called R. It's the only single attribute. My base query is select 1, okay, which gives you a table with a value 1. Okay? I union the recursive query, select R from R. And when I query this recursive relation, I select star from R. Okay, it's very simple. What does the execution look like? What the system tries to do is always start from a state where the recursive relation is empty. Okay, it's always like that. You take this empty relation, you run the things in the middle. Select 1, union, select R from R. Okay? In this case, what would you get? The base query is going to give you a relation with a single row called 1, right? Because select 1, that's what it does. You union with select R from R, which gave you empty, because in the previous step, my R is empty. Essentially, if you run this in the middle, it gave you a relation contains a single tuple 1. That's the result of your base query. And then you take this as you are, you run the two queries again. What would you have? you run the first query before the union, it still gives you 1, right? Because I mean, there's nothing else that query can do. It's select 1, right? And the union with the second part, select R from R, which gave you 1. You union them, what do you get? You get 1, right? Because union will do duplication, right? So automatically. This is the process, and then it check convergence. Okay, so it converged, right? So I run this query, it doesn't change again, right? So I mean, I get 1 in previous step, now I also get 1. So this is your answer to this query. Any questions about how the database actually run this? Yeah, sorry, cannot hear you. Can you leave it louder? So how does the system know it should be terminated? Oh yeah, so simply compare like this with the previous step. So yeah, so it's going to remember what you have in the first step, and then compare whether the result change. If the result change, it continue. If it's the same relation, it will stop and give you the answer. That makes sense? Yeah, sorry, I really cannot hear you. Sorry. Yeah. So, any questions about this? Does it make sense? Who understand the execution? Raise your hand. Who do not understand the execution? Okay, so do you have any questions? Is there any reason you don't understand the execution? Yeah.
I was expected we get 2 ones here, but we only get 1.
Oh yeah, union will do deduplication. So the union will only keep the unique element. Yeah, so that's the semantic of union. Yeah. Any other question? Who understand? Who do not understand this at this moment? It gets trickier really fast, okay? So everyone on Zoom understand this? Okay. Now let's look at another query. It's very similar to the first one. The only difference is in the recursive query, instead of select R from R, I select R plus 1 from R. That's the only difference. What would you get? Who thinks this one will terminate at all? Who thinks this one will just throw an error or just continue to run forever? Perfect. Okay, so it's very easy to think about this. You start from empty and nothing else, just empty. You run this query, you select 1, and the first step have a single tuple called 1. When you run it again, the thing before the union give you 1, the thing after the union give you 2. You union them, you get 1 and 2, right? You continue to do this, it's 3, continue, it never stop, okay? It won't terminate in theory. I mean, in practice, it will terminate. Either you kill it or database kill it. But in theory, it will never give you an answer for this one, okay? Make sense? This is not the end of it, okay? So it gets even trickier. So now let's look at this relation and this query. The difference is my query, my recursive query is the same as the previous slice, the thing that never finished. The only difference is when I query this, I have a limit 10. I only want 10 tuples from the recursive query. Will this finish? Will this terminate? What would we get? Who thinks this one will finish, will terminate? Who thinks this one will not terminate? Okay, so this is a really tricky one. In principle, right, you could go either way, depends on your semantic of like the relationship in these two pieces. But in practice, this one will terminate. So what's going to happen is you're going to start from empty, you continue have a bigger relation, and when you reach this stage that you have 10 tuples there, it's actually going to return this as an answer. Because at least for this query, the database knows I only need like 10 tuples from this recursive query, when the moment I can answer it, I will answer it. Okay? It might not be it might not be the best possible way to answer that query for you, but this is what's going to happen inside the system. Like, we can argue either way, whether this is good or not. Okay? We can construct a case that this doesn't make too much sense. But in practice, if you run a SQL query, this is what's going to happen. Okay? The system is going to decide the moment I'm able to answer your query, I answer it. Okay? Make sense? Now let's look at this one. Very similar to the previous one, but when I query this recursive relation, instead of select star, I try to aggregate over this relation. I select the minimum value of this relation. First one, I think we all know what should be the answer, right? The answer should be 1, because the minimum element in that relation is 1, right? Whenever you insert a new tuple, you only get bigger. What would the database do? Who think it will terminate? Who think it will not terminate? Okay. So again, it's very hard. This one is very hard. Yeah, so this one is super hard. Because if you think a database will terminate, you overestimate how smart a database is. As a human, we know it will terminate. The moment you give me the first tuple, I know the answer, because you're only increasing this value, right? But if you are building a database system, you will realize that's very hard to do, because you need to analyze what happens inside that query. That's something database will not do for you, because it's super hard. So what database try to do is, okay, I'm going to run this, run this, run this. I will never finish, because I can never run this aggregation. So it's assuming it doesn't have too much information about the aggregation function and about the semantic of your SQL query. It will not do really deep analysis into what you are trying to do in this recursive query in general, okay? Because that's super hard. So in this case, right, it will never terminate, because if you know nothing about the aggregation function, you cannot evaluate it without knowing the whole R, right? And that's what database try to do, okay? I think we have another example, okay? Now let's look at this one. Again, very similar to what you had before. The only thing is, now inside my recursive query, I have a condition to say, yeah, where R is smaller than 5. What would we get out of this? Who think will terminate? Who think will not terminate? So in this case, it will actually terminate. Why? Will it? I hope so. Yeah. So I can't forget. Yeah. Okay. I hope it will terminate. So essentially, like the way to think about it is very easy. You start from empty. You run that to query. You get 1, you get 2, you get 3, you get 4, you get 5. The moment you reach here, right, you continue to run. Because I have the where condition are smaller than 5, I will get something like this, and then it's the same as before. Then I have the information to actually answer this query. Okay, make sense? Another one. So we didn't go too deep into union like in the last lecture, but the difference between union and union all is union going to give you all the distinct element, okay? And union all is going to keep all the elements. So that's the difference. What if we write something similar to the query on the left-hand side? That instead of writing union there, I write a union all between these two queries. Who think it will be terminating? Who think this will terminate? Who think this will not terminate? Yeah, this will not terminate. if you think about why, is you start from empty. The first query, and the first run is clear, right? So you get something, one tuple is 1. The second one is the first query, you get 1. The second query, you get 1. You union all, you get 2 tuples with the same value, 1. You continue to do this, right? It will essentially never stop, because union all will not do the duplication for you. Make sense? Okay. So that's all the examples that we have. As you can see, it can become pretty tricky, but I think the principle is pretty clear. So any questions? No? There's one question online. So there's one question, why does it not terminate when being at 10 tuples? Can you tell me which slides that you mentioned, like which example? Let me try to get that slides. Is this a query that you talk about? Yeah. So, okay. So the question is, if you look at this query, what's the reason it will not terminate, right? So in this case, the query itself try to compute the aggregation, right? What the system, essentially the assumption and the cover is, I need the whole relation before I can aggregate it, okay? It doesn't, and the limit 10 here doesn't really matter too much, because and it doesn't matter what the limit you put. I mean, I don't know what you have when you put limit 0, to be honest, but as long as the value larger than 0, I need the whole relation until I can evaluate this query. That's my assumption, okay? Any other questions? Other questions? No? Yeah. In this case, okay, so after Easter, when we talk about how database is being actually implemented, it's very clear. So essentially what's going to happen is database has like a streaming type of model. So this query will generate tuple by tuple, tuple by tuple, and the limit will be applied to that stream. If you think about this way, is the system will try to evaluate the query without thinking about the limit side. It keep producing tuples, and then it check whether it reached the limit. Essentially here, it try to produce the first tuple. And that part will fail, because I can never produce the first tuple. Make sense? The limit is after you produce your first tuple. I don't know what happens if you put limit 0 there. That's a corner case I don't know. Yeah. But as long as the limit 1, or limit 2, or limit 100, it will wait until you have that many tuple being generated. Yeah. So that's how data, at least how PostgreSQL being implemented. Yeah. Any other questions about recursion? No? No questions? Okay. So now we have been looking at just so many different recursive queries. It's a lot of fun. But as you can think about this, it's also pretty ugly, right? I mean, this is really tricky. Compared with all the other beautiful SQL queries that we've been looking so far, this is pretty ugly. Who writes recursion in this way, right? I mean, that's weird. I mean, come on. I mean, we must agree it's weird. So, and compare with other programming language, for example, Java, for example, Python, right? So you have a very natural way to express recursion. You just call a function again, right? How hard is that? Why do we need this special construction in SQL queries to deal with recursion? So that's getting a little bit interesting, because what's the fundamental reason we need to be this ugly to support recursion? So, and also another question is, if you have a real-world application that you find yourself that you need to write a lot of recursive queries, is relational model really the right model for you? Because you are writing so many ugly queries, right? So, and that's something that we need to think about, is we talk about relational model, and we are going to continue to talk about it as if it is the only data model in the world. But it's not. Depending on the workload, depending on the data, right? If you find yourself writing a whole bunch of queries in relational model that doesn't really make too much sense, or really long, or really slow, or really ugly, make sure you kind of try to revisit your decision to use a relational model, because that's not the only data model, and that's not the universally true answer to your application. So essentially, if you look at all the previous examples, so let's think about why it is so ugly. If you look at all the previous examples, whenever we are writing this recursive query, what are we trying to do? We are essentially trying to compute a transitive closure of a graph, right? So take this flight relation, right? I mean, it corresponds to this graph. The query I'm trying to ask is pretty much the transitive closure over this graph. Why is it hard to do that in SQL query? Because when we talk about SQL, we always take a view that we are trying to answer queries that can be specified using first-order logic, right? We talked about that last week. That's the beauty of the database. That's why we get our declarative power. If you remember what you have been learning in the first year, is in first-order logic, it's super hard for you to express transitive closure. Okay, it's super hard. It's very hard for you to find a model in first-order logic that actually corresponds to the transitive closure of your interpretation. And that's the fundamental problem that we are facing right now. We take a view that the query is a first-order logic, and we are forcing the database to write something that's super hard to be expressed inside first-order logic. So what should we do if you are a database researcher in like 1980s when you see this problem? Well, we should revisit what do we mean by data, and how should we actually think about data, and how should we think about the query over my data. So we have these slides before, right? In relational algebra, the way of thinking is relational sets. Yeah, I query it as set operations. Relational calculus, my relation have more meaning. It's facts, right? It's interpretation, right? It's what I assume to be true. And my query is try to query it using logic, try to do logical inference to get more facts. Now we reach a limitation that the second view cannot support the operation that I want to do. If you are a database researcher, try to build the next generation database in 1970s, what would you have? You can always revisit what do you mean by data. Even if it's a whole bunch of things stored in a table, it have different meanings. There's an alternative data model, alternative query language, where you think about relation, try to define in a graph. Every single constant in your database is one node in the graph, and every single tuple in your relation corresponding to a hyperedge in the graph, because it tries to associate different nodes together. If you think about that, what is your query? Your query can be anything over this graph. It can be a graph pattern, right? I give you a pattern. You try to match that pattern to my database. The beauty of this, if you look at these three in the same slides, is they all have the same piece of data. It's a whole bunch of tuples in a table. But it can mean different things. It can mean a set. It can mean a whole bunch of interpretation of facts. It can mean a graph. Given how you see your data, you can have different query languages to define how to extract insight from that piece of data. Okay? So this is an alternative query language called Sparkle, which actually is much easier for you to write recursive query inside Sparkle. So we will not have Sparkle in the exam, so don't worry about that. But I really want you to see there are alternatives compared with relational model. So it's very popular in semantic web. It's actually a query language for getting information from an RDF graph. So essentially, it tries to think about data as graph and think about querying the graph or querying your data as graph pattern matching. Okay? So this is just one example database. It's very easy to see how to store this in the relational model, right? You can store this as like every single node become a constant, a value inside your database. Whenever you have, for example, like one edge in the graph, that's corresponding to one tuple in some relation. So to query this graph, right? So I think this is about football player and different clubs, right? So what you can have is you can define a like Sparkle query that look like this. It's very similar to a SQL query, but now I don't query it as logic. I query it as a graph pattern. Okay? In this case, what I'm going to have is, okay, I'm going to define the following graph pattern. That is, whatever you return to me, player and club, need to be part of the following graph pattern. In this pattern, you should have a player connected to striker using the relationship position, and that player also connected to club in the place for relation, and that club connected to a certain club, right, Barcelona, and with a region relation. This actually give you this sub graph pattern that you know the value for some of the node. For example, here you know the value here, and there are some variables here. I don't know the player, I don't know the club, something like this. And then I say, okay, now your data is a graph. My query is a subgraph. For all the matches of this query in your database, give me the value of player and the club, all the variables, and that is my answer. So this is an alternative way that you can think about how to interpret the data in relational model and how to query it. You have different query language. And it's very easy for you to write recursive queries in this, in this case. For example, you have a has-parent relation. You can say, yeah, this is the parent. So this is a child of Joe, right? So I select member where the member is connected to has-parent relation, like with Joe, right? And you can get the second level hierarchy, right? You can say, yeah. So I'm actually trying to define a graph pattern that's connected by the has-parent relation twice. And you can have a very special kind of notation. You can say, I have a member is connected by by the has-parent relation. You have star there to say I can connect it multiple times. I don't know how many times, but for all the chain in the graph that are connected by the has-parent relation, that's a match. Okay, and all of this corresponding to different essential graph patterns. The first one become the first thing, right? So I want to find this path, right? And second one is actually you jump twice. So third thing is actually you say, yeah, so I have a graph pattern. I don't care how many steps you jump, okay? But as long as it's all connected by the same relation, I'm happy. So if you compare the third query and the recursive query we have been writing in SQL, you can see the power of using a data management system when it really matches your workload and matches your underlying knowledge and data model, right? So when you start to use database for real, right, when you go find a job and use database, do not think relational model is the only thing. Whenever you get stuck, whenever it's very slow, whenever it's very ugly, and you think, oh, why am I writing that one-page SQL query for something? Maybe try to think about whether there are alternatives out there. Should I really think about my data as a collection of facts? Maybe I should think about my data as a tree. Then you have all those XML database. Maybe I should think about my data as a graph. You have a whole bunch of graph database. Maybe I should think about my database as a collection of documents, right? Then you have those like a document database, right? To you can actually phrase your query as a JSON object, something like that. right? There's a whole bunch of data management system that actually you could do. And like all depends on how you actually think about your data model and what you mean by query data. So this is actually about recursion, right? So now let's look at one example. So assuming we have two relations in my relational model, I think. You have the requires relation, contains a prerequisite and the follow-up course, these two. And then you have the lecture relation, contains all the information of different lectures. Now my query is, I want to get all the prerequisite of the database course, right? So just refresh our memory about how to write a recursive query inside relational model, not Sparkle, okay? So how should we write that? Well, yeah, we know how to write, how to not write it, right? So if you write a SQL query like this, it doesn't answer this query, right? So I think we can all see why it doesn't, because we need to find all the prerequisite course of a certain course, right? So if you join this requires table finite amount of time, that doesn't give you the answer, right? Because I want to have the transitive closure of that relation. So what should we do, right? So we won't go into detail about the SQL query, but we'll go back home, read this line by line, like line by line, and you'll see it makes sense, okay? You define a recursive relation, get all the prerequisite of a certain lecture, and then you join that with the lecture relation, and then you have a select condition to say I only care about the title equals to database, and you get the answer. Okay, so it looks very long, looks very intimidating, but if you read out line by line, it's actually not that hard to understand. Okay, so in this case, you have the base query, give you the one jump, and you have the Q2, which is a recursive query that you continue to run, right, until you converge. So that's all we have for today. So for Friday, bring your laptop here, and we are going to write a SQL query together, okay? So you will run out of things to do if you sit here looking up Visual SQL query. It's very important to practice, okay? Friday and next Wednesday, we are going to be here and write the query together, okay? I'll see you guys on Friday.